Hello students, I hope you all are safe and doing well. So today in this video, which is the 17th video in this topic of Fourier series, we are going to discuss about the complex representation of Fourier series. And till now we have discussed about the Fourier series means we have already discussed in which conditions means which type of arbitrary algebraic function we can represent in terms of Fourier series, means in terms of trigonometric functions like sine and cos. And after that we have discussed about the even and odd functions, then half range series, and these term by term differentiation and term by term integration of Fourier series. All these things we have discussed, and we have also done some problem on Fourier series. Okay, so but in these all forms we have represented the we wrote the Fourier series in terms of their trigonometric functions. So now today I want to show you how we can represent the Fourier series in complex form. Okay, and what is the advantage of this complex form representation, and how we can find that complex form of Fourier series starting with a general form of Fourier series. Okay, so when a function is given, that is arbitrary function, that is algebraic function, that can be x, that can be twice x, that can be x cube, any function, this type of algebraic function, and these functions have to be defined with some interval, can be 0 to twice pi if our variable is angle, can be minus L to L, or from 0 to twice L if our variable is representing the length. Then we can write the Fourier series in general from like a naught by 2 summation an cos nx plus bn sin nx. Okay, here x is representing the variable. If our if x is representing that length, then we can write this Fourier series like summation an, here n goes from 1 to infinity, here also 1 to infinity, 1 to infinity. Okay, cos n pi x divided by L plus bn sin n pi L x. Okay, so this way we can represent and the Fourier series in these two types of variable. Other forms are also there uh, for angular frequency. Other forms are there. Okay, those things we are not going uh, here at this point. Those already we discussed in earlier classes if you see. Okay, so this is the general form of Fourier series. So we can also write this Fourier series in complex form. Is x is the variable, x represent the variables. Then in complex form we can write this Cn e to the power I n x minus infinity to plus infinity. Okay, if you see, this is much simpler than this representation. Therefore this complex form of Fourier representation is very much useful, and you can remember this thing easily. It is symmetric. If you see minus infinity to infinity, it is more symmetric form than this form, general form. Okay, so if here angle is x is representing here angle. Okay, so if we have to write this Fourier series in terms of the variable length, then we will write fx minus infinity to infinity Cn e to the power I n pi x divided by L. Similar way. Okay, so these are the forms. So now thing is that, like in this form we calculated these coefficients using Euler relations, an, bn, we know those relations. Okay, so now we have to here, if you have been given a function and find the Fourier series in complex form, there you have to simply find the coefficient Cn. Okay, so now we are going to find this expression, this complex form of Fourier series, starting with this general form. Okay, and we will going to find this value of Cn. Okay, okay, so now I am erasing this portion. I will going to find this complex form anyway. So I will start with that easier form, means we are taking the variable as angle. So in that case Fourier series become this, and here, sorry, 1 to infinity. Okay, so here we have to use some relations, which is connecting the exponential function with the trigonometric function. Those are also Euler relations. We know if I'll write e to the power I nx, no, sorry, if I will write this, you already know, cos nx, means we are going to replace this thing cos nx and sin nx in terms of exponential function. So we can write this cos nx as 2 e to the power I x plus e to the power minus I nx. Okay, here it should be I nx. Okay, so while writing this thing, this trigonometric function in terms of exponential function, this imaginary unit I appears here. Okay, so we know this is the value -1, so this imaginary unit appears here. So this is the starting from where we are introducing these imaginary components in the Fourier series. So other for sin nx, and these relations are called Euler relations. Okay, sin nx 2i e to the power I nx minus e to the power minus I nx x, this you already know. Okay, so simply we are going to put this value of sin nx and cos nx in this relation, then it will become a naught by 2 summation 1 to infinity an minus I nx. Okay, plus summation 1 to infinity bn e to the power I nx minus e to the power I nx 2i. Okay, simply we are going to simplify this expression. If I will write this thing like this, and 1 to infinity and an 2 e to the power I nx plus summation 1 to infinity an 2 e to the power minus I nx. Okay, plus summation 1 to infinity. If I will take this numerator or this I in denominator in numerator, and this sign will become minus, so here we have to write minus here, so it will become 2 bn e to the power I nx. So here minus, this minus, both, if both will be multiplied, then it will become plus for the next term 1 to infinity 2. Okay, here it should be I 2 I bn e to the power minus I nx. Okay, so this is the things, this is the thing. So now we are going to simplify a little bit more. A naught by 2 plus summation 1 to infinity. Here we are going to take e to the power I and x common from this term and this term. Okay, so if I will take e to the power I and x common, then remaining term will be 2 will be there, an minus I bn. Okay, similarly for the last term, if I will take e to the power minus I and x common, then it will be there 2an plus I bn. Okay, so now let's see. Remember, we are going to find the Fourier series in complex form, and so now a naught by 2 plus summation 1 to infinity, in place of an minus I bn 2 divided by 2, here we are writing cn. Okay, new coefficient, and e to the power I n x, it is there. Okay, so here let me write down this thing. Cn is equal a minus an minus I bn divided by 2. Okay, so plus 1 to infinity, in place of an plus ibn we are writing c minus n. Okay, e to the power minus I nx. So c minus n a to the power n plus I bn 2. If you see, this c minus n is the complex conjugate of cn only. Here minus sign will come, it is a complex conjugate. Okay, but for our advantage we are writing this in this form. Why we are writing this form? If you do the next step, then you can understand. Okay, so a naught by 2 will be there, a naught by 2 will be there. So here we are going to write this term at this first. Okay, and here n 1 to infinity, writing 1 to infinity, in place of that we can write also n infinity to n is equal to 1. Okay, then c minus n e to the power minus n x plus summation 1 to infinity cn I nx. Why I am writing this thing like this way? If you see the next step, you can understand, because we are going to uh, oversimplify this expression. Okay, like in place of a naught by 2 we can write in place of a naught by 2 we can write c naught. Okay, so here c naught is there. So now see, here plus, if we take this negative sign out from this term, from here also we have to place this negative sign here, minus 1, infinity to minus 1. So then we can write cn e to the power I n x. How? If you see, suppose if you have been given this thing, uh, 1 to suppose 3 e to the power minus nx, then how we will write e to the power minus x, e to the power minus twice x, e to the power minus thrice x. Okay, so similar way, if you will write here n minus 1 to minus 4 here, or minus 3 here, same expression you will write e to the power minus twice x to the power minus thrice x. Okay, so same thing, therefore I am putting minus here and removing the minus from this expression. Okay, so now here this term I will write same, infinity cn e to the power I x. Okay, now I will okay, I am removing this portion here. Now if you see, we can write this term at the extreme sorry, this will be n minus infinity to minus 1 cn e to the power I n x plus c naught e to the power I 0 x. Okay, just to make this thing make these things understandable, I am writing this thing like this: summation 1 to infinity cn I n x. Okay, if you see here, it is starting from minus infinity to minus 1, then 0, then 1, then plus infinity. Okay, it is continuing. So here this here n is equal to 0. Okay, minus infinity to minus 1, then n is equal to 0, this term. So n is equal to 0 means e to the power 0 means 1. So in place of c naught, we are just writing this thing. So all these three terms, now we can write this like this: minus infinity to plus infinity. Okay, then it will contain all these three terms. Here we have to write cn e to the power inx. Okay, so if you see, this is the form required from of that Fourier series in complex form. Okay, so we have found this one, and this representation is very simpler, like in comparison to that form. Here we have to just remember it is from minus infinity to infinity cn e to the power inx. We have to remember only one Fourier coefficient. Okay, now thing is that we have to find this one. Okay, you have to, suppose you have been given one function and asked to find the Fourier series of that function in complex one, then you have to remember this expression for this coefficient. If you find that coefficient, then you can find the Fourier series in this form. You have to just put the value of cn. Okay, so we are going to find now that value of cn. This thing I am erasing. So okay, first I will write this cn. What is the expression for cn? It is an minus I bn 2. Okay, so we already know that Euler formula for Fourier coefficients. What is these relations? If we are talking about, since we are this thing talking about the variable angle, then we will write this thing 1 by pi minus pi to pi fx cos nx dx, then bn 1 by pi minus pi to pi fx sin nx dx. Okay, that thing also we can write if our function is given from x to twice pi in this type of form, defining interval, then we will write here 0 to twice pi. So it depends what type of problem you have been given. Depending on that situation, you will write this relation. Okay, it will not affect this thing. So now we'll put this thing here, uh, 2 1 by 2. I can take this thing outside. N 1 by pi summation 0 to twice pi fx cos nx dx minus I 1 by pi, okay, 0 to twice pi fx sin nx dx. Okay, so we can take this thing outside, 2 by 1 by pi outside, and 0 to 2 pi fx we can take outside, then it will become cos nx minus I sin nx dx, okay, by 2 pi 0 to 2 pi fx. We know what is the cos nx minus I sin nx, e to the power, it is e to the power minus I nx dx. We know e to the power minus I nx is equal to cos nx minus I sin nx. Okay, so now this is the expression. Now this is the expression for Cn. So you can find the value of Cn if your function is given, fx will be given, e minus e to the power minus I nx you have to put, then you can find this value coefficient Cn, and you have to put back this coefficient in this form, summation Cn e to the power I nx, okay, minus minus infinity to plus infinity. Okay, this is the thing. So you can also find the value of c minus n. So only difference is that here plus will be there, so it will be twice pi 0 to twice pi fx, here it will be I nx dx. So when this negative sign is there in the coefficient, here positive sign will there. Okay, you have to remember. So then you have to know, you will find definitely c naught will be a naught by 2, and we know this a naught value, so 1 by 2 will come. So a naught we know 1 by pi 0 to twice pi fx dx. So here no any I is there, okay, in this thing, in this coefficient. So but here you have to only find this coefficient Cn, and Cn will be sufficient to find the Fourier series in this complex form. Okay, so I hope you have understood this thing. It is very simple. You have to just remember those Euler relations, which is connecting the exponential function with the trigonometric function, that is sine and cos functions, and you can start with the general form of Fourier series, then at the end with the simplification you can find the complex form. Okay, so in the later class, next class, we'll do some problem. We will use some function, periodic function, to find that Fourier series in complex form, where we'll find these coefficients. Okay, so thank you very much. If you have not understood anything, any doubt, then you can write me in the comment section. Okay, and also please share and subscribe, share this video and subscribe my YouTube channel. Thank you very much.